Hi everyone, welcome back to the Linux. Today we are going to see about Naïve Bayes classifier. It is in a supervised machine learning used for any classification task, and it will tell us about the data, which class or which category it belongs to, and it will assume that the each input features are independent in each other in the each classes, and it is in a probabilistic model, and it will use the Bayes theorem to classify the data. So let's see the Bayes theorem. This is the equation of a Bayes theorem, and Bayes theorem uses a conditional probability to predict the to find the probability. So first let us understand the conditional probability. Conditional probability. In mathematically, the conditional probability written as p of x given y. It will read it as the p of x given y. This means we need to find the probability of an x, the already happened y. This means we already know the probability or in a that probability of an a y. We need to find the probability of an x in the y. For example, let's take an example. There are hundreds of people. Let's draw in a big circle. In that, there are hundreds of people in there, and there is some amounts of some number of people who loves in a orange juice. Let's take in a y. Y. The number of it is the number of people who loves orange juice. Let's take in a y equal to 60 number of people who loves an orange juice. Let's take 60 and let's check the x. We need to find the probability of x in given y, right? So let's take the number of peoples who loves apple juice. So the x is defined as number of peoples who loves in a apple juice, and y is defined as number of peoples who loves orange juice. In the conditional probability, it's defined as the probability of an x in given y means we need to find the probability of an apple juice in the orange juices. For example, there are hundreds of people. In that, there are 60 number of people who loves sorry who loves orange juices. In the 16 number of orange juice people, there are some people who loves both orange juice and as well as the apple juices. So we need to find the number of people who loves the apple juices in the orange juice circle. It's like it's like filtering, right? If there are in the 100 peoples, some of like 20 peoples, sorry, like 20 peoples who loves pineapple pineapple juice, and another 20 peoples who loves banana juice. But in the conditional probability, we need to it will find the x in given y means here it is the x is number of people who loves an orange juice, right? In this 100 group, hundreds of people, there are 60 number of people who loves the orange juices, right? The by the conditional probability, the y, the after the variables, after the the variable y, it's always founded, or it will tell us the y is already happened, and we need to find the x. In the conditional probability, the y is already happened, so we only need to find the x's. So as per the conditional probability, there are 60 people who loves the orange juices, but we need to find the number of people who loves the apple juices in that 60 people. This means there is a small circle inside the orange juice circle, and we need to find the probability of an apple juices this circle of people who loves the apple juices. We need to find the probability who's like number of people who loves the orange juices. It's like, let's take the example as number of people who loves the apple juices in the orange juices people. It's like 20. So the probability looks like 20 by 60 and it's 1 by 3. So in the apple juice world, there are 1 by 3%, like one of the 3 persons who loves the apple juices. This is how the conditional probability works. It's like, it's like filtering, right? There are pineapple and bananas and orange juices. And in these groups, we need to find the apple juice number of people who loves the apple juices in the specific group, right? It's like we are filtering out the bananas, banana peoples and pineapple lovers. You know, we are filtering out these groups and only focused on specified groups like given y, like given y's. It's like conditional probability of an x in given y or specified. Here it is orange juices. Here it is the number of people who loves the apple juice in the orange juice world. There are in the juice world there are 60 people. In that there are 20 people who loves the apple juices. Here it is probability is 1 by 3. And conditional probability formula looks like, let me erase this. P of x given y. This is the conditional probability. And formula looks like P of x intersection b, x intersection y divided by P of x. This is the conditional probability formula. By using the conditional probability formula, we can construct the Bayes theorem. Let me construct that. Let's take this is an equation number 1. And in the equation number 1, we take the probability of x given y. Let's reverse that. Let's take probability of y in given x. And it's equal to P of x intersection y and P of y. The x intersection y is also equal to y intersection x. That's why I written like this. And if I rewrite the equation for P of x intersection y, it looks like, if I rewrite the equation number 1, P of x given y equal to, P of x given y into P of x equal to P of x intersection y. Let name it as equation number 3. And similarly for second equation, P of y intersection, P of y given x into this P of y comes here, and P of y equal to P of x intersection y. Let's take the equation number 4. In the both equation number 3 and 4, RHS are same. So we simply equate them. Let me erase the equation number 1 and 2. If you equate them, like P of x given y into P of x equal to P of y given x into P of y. If I rewrite the equation for a probability of x given y, it looks like P of x given y equal to P of y given x into P of y divided by P of x. This equation, this equation called as Bayes theorem. You can see that here. This is a exact same equation. This and this are same equation. This equation called as Bayes theorem. But in the machine learning model, there are n number of features. So we simply find the probability each of them. This is the formula for a Bayes theorem, sorry, Naïve Bayes theorem, or we can say as Naïve Bayes classifier. If I expand this, and it will, this is wrong, it will like P of C given X. And if I expand this, P of C given X equal to, this is read as big pi, big pi. And it's similar to the, 1 minute, it is read as big pi, and it's similar to in a summation. In the, in summation we simply like add the values, but in the big pi we simply multiply the values. For a conditional probability of C given X, it's written as P of C and P of X given C divided by P of X. But in the machine learning model, there are n number of features like x1, x2, x3, up to an xn, xd. Here it is xd. So for this, we use a big pi like I equal to 0 to an d. If I expand this, P of C into P of x1 given C into P of x2 given C into P up to xd, P of xd given C and P of x divided by P of x. This is how we find the probability of a class. Probability of a data point belongs to that class. And as you can see that P of x, P of x is common and it's in a constant, right? Number of features in the models are remain same, and its probability also remains same. So it is constant, right? So, and we, it is in a constant, right? We simply remove this. Due to the removing this, we remove this equal to and give us in a proportional, because it's in a constant, right? If you are removing the constant, we given a proportional, right? In vice versa. And this is how the formula looks like. And we only needed to find these values and the probability of that classes. We simply multiply them and we finally normalize all the classes, and we found which the data belongs to which classes. Let's do some dry run. Let's take in a categorical data for better understanding of in a Naïve Bayes classifier. There are three features: outlook, temperatures, humidity, and winds, and each of its features have a categorical value like sunny, rainy, overcast, and in temperatures hot, mid, cold, and in the humidity high and normal, and in windy true or false, like there are high hair, there is no hair. And there are two classes, or we can say as two label, that is yes or no, to play the games. Let's take an example. This is in a sample data set to find the train the model and predict the outputs. Let's take in a conditional probability of each of them. As I told, P of x given y means the y is already happened, right? We need to find the x, the probability of x in that y, right? This means as per the table, these are already happens, right? These classes or yes and no's are already happens. We need to find this x. Let's see the outlook. Let's find the probability of a sunny of yes. It's like whenever the sunny comes, what is the probability? It's what is the probability we can play the game? It's the yes, right? Let me tell me. Let's tell me once again. Like whenever the sun is comes, what is the probability we can play. And second, whenever the overcast is comes, and what is the probability we can play the game. And whenever the rain is comes, what's the probability we play the game. And similarly for an a class no, whenever the sun is come, what is the probability we don't play the game, right? It can find it by the probability of sunny in given s means we can take all the s's. For example, these are the s's, right? These are the s's. Fine. These are the s's. We need to find the whenever the sun is come, what is the probability of an s, right? Let's take in a sunny. These are the sunny. So we found out the first we group the s, right? We filter out the others classes like no. We only focus on the class s, and in that yes, whenever the sun is present, the whenever the sun is present, what is the probability of a class? We play the game, right? So in that there is one sunny, there are one sunny, and second, and it is no, and it is s. So there are total of 9 s's occurs. In that there are 3 sunnies gives an s, right? So 3 by 9. Let me see again. There are total of 9 s's, right? Here it is 3 and 1. Here it is 5, right? In total there are 9, right? In that 9, what is the probability of sunny occurs? In that same time, what is the probability of sunny occurs, right? In this 9, there are 3 sunny occurs, right? So we simply written as probability of sunny in given s is 3 by 9. In similarly, we find the probability of an overcast in s. Here it is same. There are 9 s's, right? What is the probability of sunny occurs in these s's, right? Sorry, what is the probability of overcast occur in these s's? In this, there are one overcast and again overcast and again another overcast and another overcast. There are 4 overcasts occur this like this S circle. It's like there are overall like there is overall whole classes. Sorry, there are big classes. In that big classes, there is a two classes. Sorry, class S and class no. In that S, in that S, what is number of sunny suckers? We finding the number of sunny suckers. Sunny is 4, and in that we are finding the first we found the sunnies, and in this case the number of S is 9 and number of no is 4. Sorry, 5. In that is number of sunny sucker is 4, right? Number of sunny suckers 4. Similarly, number of sunny is 3. Number of sunny is 3. Similarly, number of overcast is 4, and the balance one is number of rainy, right? In that rainy is there is 2 rainy present in the S class, this one and this one. These 2 rainies are present in the S block. There are 2 rainies. It's like filtering, right? They are in the S classes. What is the probability of sunny? In the S classes, what is the probability of overcast? Similarly, in the S classes, what is the probability of overcast? We similarly do for no classes also. In the no classes, like in the no classes, what is the probability of sunny? For example, let's take let's take no classes. These are the no classes. No, no, and there are five entities. There are five entities in the no classes. So there are five in that five entities. Or in that five, how many of them are in sunny? How many of the overcast? How many of it's rainy? For example, there is one sunny and there is another sunny. In the five, there is two sunnies, right? There is two sunny, and there is in the test. Let's take number of rainies. Like there is one rainy and there is three rainy. If you can see that there is no overcast. All the no classes, there is no overcast. So in the no classes, there is two block for an A sunny, two like two sunny occurs in the no classes and three rainy occurs in the no classes. We simply written like this. Here you can see this, there is no overcast. We similarly do for, we are finding the probability of an A yes and no classes to its overload. Similarly, we do for an A temperature, and similarly we do for an A humidity, and similarly we do for an A wind. And you can do that calculation by pausing the video. And this is how the probability of an A remaining terms looks like. Fine. After finding this, we need to, if the new inputs like, let's take x equal to sunny, hot, and normal, and false. It's like the overlook is sunny and temperature is hot, and the humidity is normal and windy is false. What is the data? It's an input, right? It is a temperatures of a circumstance, and we need to find if the players will play the game or not, right? Based on the past data like this, based on the past data, we need to find whether this input, whether this condition, the player will play or not. We found the probability of an data, and each futures are independent to each other. So we find the probability of each independent futures, and these are the probabilities. We are calculated that, and we need to predict the output, right? So let's try that. So the input like sunny, normal, sunny, hot, normal, and false. First, we find the probability of S in given X. X is this, right? And the as I told, the formula looks like P of X given Y is P of X into P of Y given X divided by P of Y, right? This is how it looks like. But due to the P of Y it's constant, we simply neglect them, and instead of putting equal to, we simply put the proportionals. So we neglect some time complexities. And here it is P of Y in given X. It looks like P of X, P of S into P of sunny. Yes, it's like number of S will occurs, number of sunny occurs in that S, and into number of odd occurs in the S world, right? S world, and we can say it as into number of normal occurs in the S world, and we can number of false occurs in the S world. We substitute this formula by here. Let me erase this. P of sunny, no. if we see the P of sunny S, that is 3.9. Sorry, it's looks like it's a mistake. Looks like 3.9. Sorry, 3 by 9. And also, and P of R in given S is P of R in given S is 2.9. So we written as 2.9. And P of U normal in given S is P of normal in given X is 6.9. And also P of windy, sorry, P of us in given S is P of us in given S is 6.9. And if I multiply this, this is an answer we get. And similarly, we do for an P of no classes. After finding the probability of a data belongs to each classes, we do some normalize it. So it will tells the probability of a data belongs to in each classes, and overall probability is 1. This is how we do in a normalization. First, we add the total probabilities, like probability we get in for an S classes and probability we get the for an no classes. If you multiply them, this is the answer. This is an overall probability, right? And in that, what is the probability of an S in given input? It's like we divide the overall probability, that is 0.2796, by the probability of an X belongs to that classes, right? That is 0.02116. That is full, right? That is overall full probability. And this is probability of data belongs to in class S, right? This means it will give some ratio, right? 30%, 60%, like that. And that is 0.756. And similarly, we do for an a class 2, that is overall probability is 0.02796. And probability of data points belongs to no classes is 0.00680, right? And it will also give some ratio, that is 2.46. If you sum them up, like 0.756 and 0.244, it's always equal to 1. This is 1, and sorry, this is 0 and 1 goes there, and this also 0 and 1 goes there, this also 0 and 1 goes there. If you can see that the sum of the probability of normalization, sorry, normalization, so always 0. See, sorry, it's always 1. So using the normalization, we found the ratio or percentage of data, or we can say as probability of data points belongs to each classes. In this case, the 0.756 is greater than the 0.244. So the data belongs to the probability of 0.756. That is the probability of S classes. In this case, the player will willing to, or he will play the game. This is the how the model will trained, like finding the probability each data independently and finding its probabilities, and Bayes theorem based on the Bayes theorem, we will find the probability of data belongs to each classes, and we similarly do for all other classes. After the finding the probability belongs to each classes, and we do some normalize to get the ratios of data points or data points to belongs to each classes, and overall probability of a normalizes it's always 1. And this is how we find the Naïve Bayes classifier will works. There are 3 main types of Naïve Bayes. In this example, we use the categorical data, right? Each inputs are categories like rainy, sunny, overcast, hot, cold, mild, right? These are the categorical data. But in the real world application, there may be some continuous values or maybe in a discrete values, right? In the case, we use in this, like the probability function, we simply find the frequency, right? In the probability function, we simply found the number of s it occurs, and in the test number of sunnies, or in the test number of rainy, we found that, right? We found that in the terms of frequency, right? But in the real world example, there may be cases the categorical data, there is no categorical data. There is only in a, like there is continuous variables or in a discrete variables, right? So in that case, we use in a Gaussian. There are three types: Gaussian Naïve Bayes and binomial Naïve Bayes and Bernoulli's Naïve Bayes. These are the data for a continuous random variables. We use something called Gaussian Naïve Bayes, and similarly for a discrete, we use some other Naïve Bayes algorithms. For a categorical data, we simply find the probability by a frequencies of occurrence class. But for a continuous values, like minus infinity to plus infinity, the data occurs in that intervals. So we don't find any like frequency in that because it's continuous, right? We don't have any frequency in that. So in that case, we use some distribution formulas in these in the types of Navy bias to calculate the data into any categories. These are the three main types. In upcoming videos, we will understand each of its types and its applications and intuition behind them. Advantages and disadvantages. It is easy to implement and compute the computational effectiveness, and effective in the case which in a large number of features, because it's like it will it's assumed that each features are independent to each other. So output of in a one features or probability of in a one features doesn't affect another features, right? So that's why it's in a computational effectiveness, and it's performed well even within a limited training data, and it performed well in the presence of categorical features. In the categorical features, we saw that it will works well. There may be no misclassified in the model. Works well in the categorical data, and for the numerical features, data assume that it comes from the normal distributions. And there is a disadvantages also, and it will assume that features are independent. But in the real world, there may be they may not always hold the real world data and can influence by irrelevant attributes like noises and attributes, or there is some like data is wrong, and may assign the zero probability to an unseen event, leads to a poor generalization. This may occur like the conditional probability, right? P of x given y, right? This looks like P of x into P of y given x and P of y, right? What if the probability of y is zero? Then the equation looks like something P of x into P of y given x divided by 0, and it's give us infinity, right? This is not true, right? This is not true. That's because the denominator of the probability of a denominator, it's always greater than 1. We must hold this true to give in a better result. This is a major disadvantages in the Navy Bayes theorem. That's it from this video. Thank you.